New coating test improves conductivity of lithium-ion batteries in under 5 minutes. New testing method reveals ideal lithium-ion battery slurry conditions for stronger electrode performance. Scientists in Japan have developed a new way to monitor lithium-ion battery slurries during manufacturing, helping identify coating conditions that improve battery performance before cells are even assembled. Researchers at Tokyo University of Science used an upgraded rheoimpedance spectroscopy technique to study how conductive networks form inside battery slurries under industrial-like coating conditions. The method combines shear testing with electrochemical impedance spectroscopy, allowing the team to observe electrical behavior while the slurry is moving. Battery slurries are mixtures of active materials, conductive additives, binders, and solvents that later become battery electrodes. Their internal structure plays a major role in conductivity, stability, and charging performance. But most existing evaluation methods examine slurries in static conditions rather than during real manufacturing processes. The team focused on lithium iron phosphate cathode slurries and applied shear forces similar to those used in industrial coating lines. At the same time, they measured how electrical signals move through the material to track changes in the conductive network. Conductive networks under shear. The experiments showed that coating speed had a major impact on battery performance. At low shear rates, conductive additives remained clumped together, creating weak electrical pathways. At very high shear rates, the conductive network broke apart, also hurting performance. However, the researchers identified a middle range around 50 seconds to the power of -1 where the conductive additives became evenly distributed while still maintaining strong electrical connections. Electrodes produced under these conditions showed lower resistance, improved charge-discharge behavior, and better cycling stability compared to electrodes made under lower or higher shear rates. By reproducing shear conditions close to those used during electrode coating and evaluating the slurry in situ, we can relate the slurry state to the conductive network formed after drying and to battery performance, said Associate Professor Isao Shitanda. The researchers used a rotational rheometer to simulate coating conditions with a thickness of 500 micrometers. The slurry contained lithium iron phosphate as the active material, acetylene black as the conductive additive, and a polymer binder dissolved in solvent. The team then dried the tested slurries into electrodes and assembled them into battery cells for further performance analysis. Microscopy studies confirmed that intermediate shear conditions created the most balanced conductive structure. Faster battery production insights. According to the researchers, the method could reduce trial and error steps in battery manufacturing by allowing developers to evaluate coating conditions directly from the slurry stage. This method can identify promising coating conditions using less than 1 milliliter of slurry, with each measurement completed in about 5 minutes, Shitanda said. The approach could also help battery manufacturers reduce material waste and shorten development cycles, as demand for lithium-ion batteries continues to grow across electric vehicles, electronics, and energy storage systems. While the results were demonstrated using lithium iron phosphate batteries, the researchers noted that additional validation across other battery chemistries and cell designs will still be required.